Hello everyone, welcome to this lecture, Organic Spectroscopic Analysis. In this graph, we have learned radio wave for NMR spectroscopy, infrared for the transitions of vibrational states, UV for transitions of valence electrons, and X-ray for the transition of core electrons. And in this lecture, we are going to study X-ray diffraction. As we mentioned in the MS chapter, J.J. Thomson discovered the electrons by a cathode tube. As we all know that Roentgen discovered X-rays, Roentgen's wife had placed her hand in the path of X-rays which Roentgen created by beaming an electron ray energy source onto a cathode tube. Roentgen's discovery of these mysterious rays capable of producing an image on a photographic plate excited the scientists of his day, including Becquerel. Becquerel found that while the phenomena of fluorescence and phosphorescence had many similarities to each other and to X-rays, they also had important differences. While fluorescence and X-rays stop it when the initiating energy source was hottest. Much to his Becquerel's surprise, the plates were exposed during storage by invisible illumination from the uranium. Illuminations did not require the presence of an initiating energy source. The crystals emitted rays on their own. Although Becquerel did not pursue his discovery of radioactivity, others did, and in doing so, changed the face of both modern medicine and modern science. Atomic particles. Rutherford's work showed that consisted primarily of empty space surrounding a well-defined central core called a nucleus. In a long and distinguished career, Rutherford laid the groundwork for the determination of atomic structure in addition to defining the planetary model of the atom. He showed that radioactive elements undergo a process of decay over time. Taking together the work of Becquerel, the Curies, Rutherford, and others made modern medical and scientific research more than a dream. They made it reality with many applications. A look at the use of isotopes reveals just some of the ways in which the pioneering work of these scientists has been utilized. 17 years after the discovery of X-rays in 1912, the German physicist Lohr discovered and recorded the diffraction of phenomenon that occurred when X-rays passes through crystals. Sir William Henry Bragg and his son Sir William Lawrence Bragg determined the first mineral structure, which is the sodium chloride, from XRD. In Bragg's law, incoming X-rays diffract from the crystal plates. Reflections must interface for a detectable signal. Once we know that spacing between the plates d, we can work out the lattice parameters. Measurement of crystal angle theta c allows computation of interplanar spacing d. X-rays are electromagnetic radiation occupying the spectrum from about 10 to -2 power to 10 to 2 power angstrom in wavelengths. X-rays can be described in two ways: electromagnetic wave and particle or photon with energy proportional to frequency. X-rays are produced when high-energy electrons bombard a metal target, interacting with its atoms. The potential difference across the X-ray tube accelerates the electrons from the cathode to the anode, increasing their kinetic energy as Ke. The potential difference across the tube may not be constant, hence the use of the term kPb for peak. Therefore, the amount of kinetic energy gained by each electron may differ. An X-ray machine like that used in a doctor's or a dentist's office is really very simple. Inside the machine is an X-ray tube. An electron gun inside the tube shoots the energy electrons at the target made of heavy atoms, such as tungsten. X-rays come out because of atomic processes induced by energetic electrons shot at targets. There are two different atomic processes that can produce X-ray photons. One is called breaking radiation. The other is called characteristic radiation. Binding energy is the energy which binds the electron to the nucleus. The energy must be supplied to the electron in order to remove it from its orbital shell. Excitation results in an outer shell electron gaining energy and being raised to a higher level. Heat is produced as the electron falls back into its original path, and the filament electron may repeat its process many times. Outer shell electron ejected from target atom. Ionization takes place, resulting in an outer shell electron being completely removed from the target atom. This type of interaction may cause the target material to heat up. Inner shell electron ejected from atom, electron falls to occupy a vacancy and burst of X-ray emission. In 1913, Henry Moseley discovered that the wavelength of an X-ray depended upon the nuclear charge of an atom. The K-alpha and K-beta transitions are the most likely to occur, producing X-ray photons of about 58 and 68 keV. Until Moseley's work, atomic number was merely an element's place in the periodic table and was not known to be associated with any measurable physical quantity. The incoming electron transfers sufficient energy to remove an inner shell electron from its atom inner target. In order for this to occur, the electron must process energy at least as great as the binding energy of the inner shell. The inner shell vacancy is quickly filled by an electron falling inwards from a shell further out from the nucleus. This transition is accompanied by a burst of electromagnetic radiation with energy equal to the difference in binding energies of the two shells. This type of X-ray production is termed characteristic because the exact photon energy is characteristic of the element of which the target is made. In summary, characteristic X-rays are produced by transitions of orbital electrons from outer to inner cell. Since the electron binding energy for every element is different, the characteristic X-rays produced in the various elements are also different. This type of X-ray radiation is called characteristic radiation because it's characteristic of the target element. The effective energy of characteristic X-ray increases with increasing atomic number of the target element. Characteristic X-rays contribute less than 10% of an X-ray beam. The majority of X-ray production results from inelastic collision of incoming electrons with the nuclei of the target atoms. The incoming electron passes very close to the nucleus of a target atom. The attraction causes the electron to deviate in its course. The sudden change of the direction stimulates the electron to release energy in the forms of a photon of electromagnetic radiation. This emission of radiation results in a reduction in the electron's kinetic energy, causing it to slow down. The energy of radiation depends on the degree of deviation the electron suffers. In an extreme case, the electron may actually be brought to rest. Thus, the photon energy can be one of any value from 0 up to a maximum equal to the initial kinetic energy of the incoming electron. This gives rise to a continuous spectrum of X-ray radiation and is known as a breaking radiation. Inelastic processes are much more likely to occur than characteristic or breaking processes. Less than 1% of the energy in an X-ray tube is converted into X-rays. The rest is heat. At higher voltage, the efficiency is higher and relatively less heat is produced. Characteristic X-ray production cannot take place at all if the X-ray tube voltage is insufficient to give electron enough energy to remove the inner cell electron from the target atom. With a tungsten target, voltage below about 68 kV cannot produce tungsten characteristic radiation. In other materials, such as molybdenum, the voltage value required to produce characteristic radiation is much less, approximately 27 kV. The amount of heat produced within an X-ray tube can cause problems. Okay, that's today's lecture. We'll continue to learn X-ray diffraction in the next class. See you.